Before we dive into writing code, let's understand the purpose behind each step we're about to take. Step 1. Importing necessary libraries. Firstly, importing libraries in Python is crucial. It's like opening a toolbox before starting work. These libraries give us access to pre-built functionalities and tools that make our coding tasks easier and more efficient. Step 2. Generating a synthetic dataset. Moving on, generating synthetic datasets is a smart move, especially when real-world data is hard to come by or expensive. Step 3. Combining features into a feature matrix. Next, we need to organize our data into a format suitable for our machine learning algorithms. We do this by combining our features into a feature matrix. Think of it like arranging pieces of a puzzle where each row represents a student and each column represents a feature. Step 4. Splitting data into train and test sets. Now we're splitting our data into training and testing sets. Why? Well, we need to see how well our model performs on data it hasn't seen before. This helps us avoid overfitting and gives us an idea of how well our model will work in the real world. Step 5. Training the gradient boosting classifier. Time to train our model. We're using a gradient boosting classifier, a powerful ensemble learning technique. It's like building a strong team by combining multiple weaker players, or in this case, decision trees. We'll tweak some hyperparameters like the number of trees and the learning rate to train our model to recognize patterns and relationships in the data in this step. Step 6. Predicting on test set. We're using it to make predictions on our test set, which helps us see how well our model generalizes to new, unseen data by comparing its predictions to the actual outcomes. Step 7. Calculating or printing the accuracy. This tells us how often our model's predictions are correct compared to the actual outcomes. It's like grading our model's performance. The higher the accuracy, the better our model is at predicting. To start off by giving an overview of all the codes we'll be using for this activity, let's start with our first set of codes, importing the necessary libraries. Let's call it set 1 for simplicity. Okay, so for line 1, this imports the NumPy library and allows you to refer to it as NP in your code. NumPy is a library for numerical computations in Python. And for line 2, this line imports the gradient boosting classifier class from the sklearn ensemble module. sklearn is a scikit-learn library which provides tools for machine learning in Python. Next, line 3, this line imports a train test split function from the sklearn model selection module. This function is used to split datasets into two subsets, one for training the model and the other for testing the model. Line 4, this last line in the set imports the accuracy score function from the sklearn metrics module. This function is used to compute the accuracy of a classification model by comparing the predicted labels with the true labels. On to set 2, where we'll be generating a synthetic dataset. Line 1 of this code set, np random seed 42, sets the random seed for NumPy's random number generator. Setting a seed ensures that the random numbers generated are reproducible, meaning they will be the same every time you run the code. Line 2, our num students is assigned the value of 2000, sets the number of students in the synthetic dataset to, well, 2000. Next, line 3 generates an array of study hours for each student using NumPy's random uniform function. It creates random floating point numbers between 0 and 10 for each student. Line 4, on the other hand, generates an array of previous exam scores for each student. Similar to study hours, it generates random floating point numbers, but in this case, they are between 0 and 100 for each student. Line 5, this last line of code generates an array indicating whether each student passed or failed. It randomly selects either 0 or 1 for each student. Moving on to set 3, or combining features into a feature matrix. With a single line, the line creates a feature matrix. We'll call it variable x. This line creates a feature matrix by combining the study hours and previous exam scores arrays horizontally using NumPy's column stack function. Each row of variable x represents a student, and the first column contains study hours, while the second column contains previous exam scores. On to set 4, or splitting data into train and test sets, again with a single line of code. Remember line 3 of set 1? Set 4 is actually where we will be making use of the imported function in the specified line. Going back to set 4, this sole line of code in this set splits the data into training and testing sets using the train test split function. It takes the feature matrix variable x and the target variable passed, along with some parameters. Point 2 being assigned to the test side specifies that 20% of the data should be reserved for testing and the remaining 80% will be used for training. 42 being assigned to the random state variable serves the same purpose with line 1 of set 2, setting the random seed for reproducibility. The only difference will be is that it is used when initializing models or functions in scikit-learn, such as train test split or classifiers like gradient boosting classifier, while the specific code in line 1 of set 2 sets the random seed specifically for NumPy's random number generator. This affects any random number generation operations using NumPy, such as generating synthetic data. Now, to train our gradient boosting classifier or set5, it is essential that we remember line 2 of set1, as without importing the necessary libraries that we did in line 2 of set1, we would not be able to use the necessary functions required in this set of codes. Okay, going back, this line trains the gradient boosting classifier using the gradient boosting classifier class imported earlier. Parameters for the classifier are as specified. 100 is assigned to the n estimators variable, which sets the number of trees or boosting stages to 100. Next, a 0.1 value is assigned to the learning rate variable, which then controls the contribution of each tree in the ensemble. Lower values generally require more trees but can lead to better performance. Next, the max depth variable being assigned the value of tree sets the maximum depth of the trees. The last parameter, the random state variable being assigned the value of 42, again sets the random seed for reproducibility. Onto line 2 of set 5, the fit method, a common method used in many machine learning libraries, used to train a machine learning model on a dataset, is called on the classifier object, passing xtrain and ytrain as arguments. As just been mentioned, this trains the classifier on the training data. Up next, set 6 or predicting on test is a quick and easy step. GB classifier predict xtest being assigned to ypred predicts the labels for the test set using the trained classifier. For the last step, set 7 or to calculate and print the accuracy, it is also important to note that without line 4 of set 1, we wouldn't be able to run our code and get our expected output since this set involves the accuracy score function. Okay, so for the first line of our last set, this line calculates the accuracy of the model's predictions by comparing the predicted labels ypred with the true labels ytest using the accuracy score function. To finish up our last code, the print function prints out the accuracy of the model on the test set. Since we're done, let's now run our code. Okay, so the output of 0.505 represents the accuracy of the trained gradient boosting classifier on the test set. A few reminders. Accuracy is a measure of how many predictions the model got right out of the total number of predictions made on the test set. In this case, an accuracy of 0.505 means that the model correctly predicted the outcome for approximately 50.5% of the samples in the test set. Since the output is around 0.5, it suggests that the model's performance is not much better than random guessing. In other words, the model is not performing well on this dataset. This could be due to various reasons, such as insufficient data, inappropriate choice of algorithm, or insufficient tuning of hyperparameters. In practice, you would typically aim for a higher accuracy, ideally well above 0.5, depending on the specific requirements and complexity of the problem you're trying to solve. To improve the model's performance, you may need to experiment with different algorithms, adjust hyperparameters, gather more data, or perform feature engineering to better represent the underlying patterns in the data.